Pressure-based mass flow controllers are based on the Hagen-Poiseuille equation. This physical law describes the pressure drop in an incompressible fluid with a laminar flow through a long cylindrical pipe of constant cross-section and can also be extended for use with compressible fluids or gases. By measuring the upstream pressure and downstream pressure across a laminar flow element, this equation can be used to relate these measured pressures to the actual mass flow. A traditional PMFC approach includes an upstream pressure transducer to measure the supplied pressure, an upstream control valve, two individual absolute pressure transducers, and a laminar flow element. The two individual absolute pressure transducers and the laminar flow element work together to measure the pressure drop. This information is then used to derive the mass flow rate. This approach is proven and is less sensitive to supply pressure variations. However, the use of the upstream valve opens up many disadvantages. This design requires high pressure, making it suboptimal for critical low-pressure gases and low full-scale flow rate. This also means the two individual pressure transducers must be perfectly matched. By nature, all transducers exhibit some level of change over time. If they change by different amounts or in opposite directions, the product will become increasingly inaccurate as these offsets are squared in the mass flow rate calculation. We can do better. To address these limitations, a new design approach is needed. The foundation of the GP200 PMFC is our patented integrated differential pressure transducer module. The same equation can be rewritten to utilize a true differential pressure measurement instead of two individual absolute pressure transducers. Going from two separate transducers to one true differential transducer enables us to rewrite the equation. The GP200 replaces the need to match P1 and P2 by using a true differential pressure sensor. By rewriting the equation, we're able to measure the true differential pressure versus a derived differential pressure using discrete P1 and P2 values. This reduces measurement uncertainty and improves accuracy, particularly for critical low vapor pressure process gases. The K factor in the equation is an empirical constant dependent on the temperature, viscosity, and compressibility of the gas, and the geometry of the laminar flow element. Combined with the downstream valve architecture, this enables the GP200 to operate at much lower inlet pressures and across a wider range than other pressure-based MFCs. The downstream valve also removes the bleed-down effect and ensures the device is insensitive to dynamic outlet conditions. The integrated electronics in the GP200 process the data that is received from the differential pressure sensor and compare it to the given set point. The GP200 is constantly monitoring fluid property changes as a result of any temperature fluctuations and compensates for these changes in real time. Fluid properties are updated for temperature and pressure changes every 2 milliseconds to ensure process gas accuracy under real-world application conditions. This is accomplished by embedding the dynamic gas model in the GP200 device, where the governing fluid mechanics equations are solved in real time at every signal processing cycle. The GP200's sophisticated control algorithms use logic from the integrated electronics to drive the valve open and closed to allow more flow or less flow. The GP200's unique product architecture provides many advantages over traditional competitive PMFCs currently in the market and is setting the standard for what it means to be best in class. The GP200. All of the performance, none of the limitations.